A tiny deviation, like a single degree off perfect, might seem harmless on a standalone component. But when that aerospace bracket mates to a larger assembly, that misalignment prevents the mounting holes from aligning, concentrating the load onto a single fastener. This diagram shows the math behind standard angular tolerancing. If we allow an angle to vary by plus or minus 1 degree, we create a wedge-shaped tolerance zone. The further that surface travels from its starting vertex, the wider the error margin grows. A part that meets specifications at its base can exceed those limits at its far edge. To eliminate that expanding margin of error, we use the GD&T Angularity control. It belongs to the orientation family, sitting alongside parallelism and perpendicularity. Securing large, interconnected assemblies requires using rigid, linear boundaries. This method maintains a constant error margin across the entire length of the feature. This two-dimensional draft details a part with a slanted face, anchored to our baseline, datum A. A frequent error in reading these drafts is assuming the tolerance for this slant is measured in degrees. Before applying any tolerance, we have to define the exact theoretical angle. We do this using a basic dimension, represented on the drawing by an angle that is strictly boxed in, like this 45 degrees. Once that perfect angle is locked, the tolerance zone is constructed around it. This zone is formed by two perfectly parallel planes, separated by a strictly linear distance, in this case 0.1 millimeters. When the part comes off the manufacturing line, the physical surface will be irregular. To pass inspection, every peak and valley of that jagged real-world profile must fit entirely within that linear 0.1 millimeter gap. Because those boundary planes are perfectly parallel to each other, the allowed deviation never expands. Whether the part is 10 millimeters long or 10 meters long, the physical surface is constrained to the exact same linear error margin. This logic applies internally, too. This wireframe displays a hydraulic manifold block with an internal cylindrical channel intersecting the center. When we add a diameter symbol to the feature control frame, the geometry of our tolerance changes. We are no longer dealing with two flat planes. The boundary becomes a three-dimensional cylinder, projected strictly along that precise basic angle. Verifying this on the shop floor requires precise metrology. Coordinate measuring machines map the internal points of the physical hole to calculate a derived median line. As long as that calculated axis stays entirely inside the translucent tolerance cylinder, the part is compliant. Look closely at this blueprint for an automotive suspension arm. It calls for an angularity tolerance of 0.05 relative to datum A, but the angle itself is written as 45 degrees plus or minus 0.5 degrees. Combining traditional plus-minus degrees with modern GD&T orientation controls creates a mathematical contradiction. Without a boxed basic dimension to lock the center of the parallel zone, the shop floor cannot anchor the boundaries. The drawing becomes impossible to accurately inspect. This aerospace weldment features an angled mounting plate referencing datum A at the base. You'll quickly see why relying on a single primary datum is rarely enough to secure a component like this. Referencing datum A anchors the specific tilt. However, it leaves the rest of the geometry unconstrained. The entire parallel tolerance zone is free to spin around the vertical axis like a weather vane. To eliminate that rotational freedom, we introduce a secondary datum, like a side edge or a pin. Once we reference datum B, the tolerance zone snaps into a rigid orientation, preventing any lateral twisting. This gives us three strict rules for angularity. 1. It requires basic dimensions to establish the theoretical angle. 2. The tolerance zone is always linear, either parallel planes or a cylinder. And 3. It controls the tilt of the feature, not where the feature is physically located. That last rule is crucial. Angularity ensures your tilt is precise, but a perfectly angled hole drilled half an inch off target is still a scrapped part. Controlling that exact physical placement requires a different tool entirely, position tolerancing. And that is what we will cover next.